Welcome to the GreenTalk. Yeah, I'm really happy to be introducing Sonia Travaglini. Sonia is a very young PhD researcher. She's doing her PhD at University of Berkeley. And she did her undergraduate, she has a Bachelor of Science, and she was majoring in materials and design at the University of Portsmouth in England. She did a Masters of Science working on recycling polymers. As you can see, she has a lot of letters behind her name for somebody, and I was asking how you do that. So she's a member of many engineering and engineering design societies. She has a lot of interests, and she's going to mention probably just a few of them. One of them is sign language, and it might be US sign language that brought her over here. And she has this interest in mushrooms or mycology, and she's going to talk today about designing new materials from fungi. So please give her a warm welcome. Thanks, Sonia.
Thank you. Well, thank you very much. Good afternoon, everyone. My name is Sonia Travaglini, and I'm here to talk to you today about mycology materials. First off, I'd like to say thank you so much for inviting me here today to San Jose State University, and it's a pleasure to talk to the engineers of the future. First, I want to get a sense of who's in the room. I know we're all engineers here. Have we got any mechanical engineers in the room? Hands up if you're mechie. Hey, go mechie. How about EECs? Any electronic engineering in the room? Oh, pretty great, nice. Any environmental, design or civil? A couple, excellent. Well, thank you so much for joining me here today. We're going to talk about a few different fields. We're going to talk about mechanical engineering. We'll probably touch on a few other bits of engineering, including civil engineering. So my email is travaglini@berkeley.edu. As you can imagine, I'm with the University of Berkeley, University of California, Berkeley. And if you have any questions at any point, do drop me a line via email. I'm also always doing outreach in engineering because I'm a really passionate supporter of education in engineering. And I know all of you are going to go on to masters and PhDs, of course. There will be time for lots of questions at the end, so if you have a question, do keep it in mind, and we'll deal with those in a little bit. So, an overview today. We're going to talk about quite a few things. We're going to talk about these mushroom materials themselves. There's an example up here, if you want to check them out. We're also going to talk about exactly how are these materials made? What are they made of? What are they actually comprised of? I'm also going to talk a little bit about how I came to get into engineering and how I ended up engineering mushrooms. I'm also going to talk about the applications they have, so where these are actually being used right now, today. And finally, I'm going to talk about the future opportunities these materials can afford us. So without further ado, let's get into it. Obviously, we're talking about mushroom materials. That's fungi. They're quite interesting materials because they're grown from waste. This here is the mushroom we actually use, Ganoderma lucidum. And fungi are quite interesting because they actually digest waste. So what they eat to grow themselves is carbon, and they can take this carbon in from all sorts of sources. The fact that they can grow from waste means they're a very low impact material. That means they don't take a lot of energy to manufacture. That's really important when you get up to big scales of materials. And of course, being comprised entirely from a natural material, they are compostable. So once you're finished with them, you can just put them into a compost pile and they'll degenerate into another useful resource. This is the material right here. As you can see, it's really quite like a wooden brick. One interesting thing about them is they're very, very light. These fungi materials are typically, although they are comprised of some of the wooden feedstocks, made of chitin. And they have a lot of airspace in these materials, and I'll talk about that later. This lightweightness of the material is a real advantage because it means you can basically save weight. And saving weight normally means saving money in engineering. So these materials, as I said, are made from fungi, mushrooms. We all know mushrooms. Maybe you have them in your morning fry-up. Maybe you enjoy a nice veggie burger with them. But in this case, we use them for materials. They are a unique kingdom. They're neither a plant nor an animal, but they do have properties of both. As I said, they digest organic materials. So they'll go off, find some food they like, and each mushroom has a particular food they're keen on. Some of them like sawdust, carbon containing there. Some of them like different types of dead wood. Some of them even like plastics. That's right, there's even species of fungi that can digest plastics. Very good for recycling. And that's what they do, really. They're nature's recycler. They'll go off and break down any carbon that's sitting around in the general environment and turn it into something useful. Where engineering comes in is we take that and use it to make a material. This is the one we work with, Ganoderma lucidum. It's also known as reishi. This is quite a common mushroom, actually, and is used extensively in Eastern medicine. We like it particularly because of this shiny, nice surface of the material. This means when it grows, we can select the properties we want, either being a nice soft kind of external material or a very hard, shiny, hard material that you could use for more reinforcing properties. Now, as I said, these materials are really useful because they're low energy. This means that we can use it to digest byproducts from agriculture, for example, sawdust from milling, or the leftovers from bioprocessors. This means that it reduces the manufacture cost. As you know, when you produce a material or a product, its life cycle analysis shows that its manufacturing is some of the heaviest impact on that. And in our modern world, where we're slowly experiencing scarcity of resources and costs are going up, we're really looking for more efficient materials. This is awesome because it's a low energy production. Mushrooms like to hang out in fairly woodsy kinds of places where they're nice and shaded. They don't typically need a lot of light. They don't need a particularly hot environment. All of that means you don't need to grow them in very intensive conditions. That means you can save money when you're actually producing them. This is important when you scale up. If you're making a small amount of material, perhaps for a short production run, it's not too much of a problem if you have a heavy manufacturing phase in your life cycle analysis. But if you're scaling up to the sorts of hundreds of tons of material needed, say, in the automotive industry or the civil engineering industry, quickly you find that saving energy on production is a very good idea. A lot of the research we do at UC Berkeley is exploring these materials. Up until now, no one had really explored their science. They've been used in artisan and industrial functions for a little while, but no one has sat down and found out just how strong a mushroom is. And that's a lot of what we do. We inform the development of these materials. I personally really enjoy destructive testing, which you may have already done as part of your degree. I put these materials into machines, squish them, poke them, squash them, and get characteristics out, how strong they are, how tough they are. All of this creates materials data, which is very important for designers. If you're making a mushroom chair, you're going to want to know how strong it is, and for that you need materials data. We also like to publish this information. It's really important to communicate your science, and so for that we tend to make journal publications. We write in more popular science, Scientific American and publications like that. And we also like to gather researchers together, just like we're doing here today. Now I'm going to tell you a little bit more about how I came to be researching this topic. As you can imagine, getting into mushrooms, researching mushroom materials, is maybe an unusual path to take as a mechanical engineer. Well, right now I'm studying a PhD in mechanical engineering at UC Berkeley. A lot of this is to do with the mycology research, as well as classes and any interesting courses I like there. And something we really work on is strengthening the links between academia and industry. So a lot of these materials are used by artisans and people in industry who are creating all sorts of things. And they need our help at universities to explore these materials, find out how strong they are, and get the information they need in able to be using them effectively. Now, I didn't quite start in mechanical engineering. I actually started in product design and innovation. And if you hadn't already noticed, I am from England, and that was where I did my original degrees. I was fascinated by design. I really like to explore new ways of using products, new ways of finding original materials that can improve our lives. I then got interested more in polymers. I started to get fascinated by the many different uses of polymers, their different properties, how they can be tough and strong at the same time. And that led me eventually to a Master's of Science in Advanced Manufacturing Technology. Now from there, I really enjoyed all of the academics. And what I really was interested in is using different fields together. So one of these interesting things about fungi is they're really taking two fields and putting them together. This is known as biomimicry, using principles from nature to create new materials. So what we do is we'll take a concept such as mushrooms and how they grow, and we'll engineer that in order to be able to get to an actual material you can use for a chair. As I mentioned, I enjoy the destructive testing. So what I like to do as part of my research is I put these materials into a machine, a compressive tester, and I'll crush them and see just how strong they are. I'll put them into a tensile machine, and I'll pull them and stretch them to see what their tensile strength is. We also had a look at how tough they are, just how much energy can they absorb before breaking. Out of all of this, I then write up all this information into a technical publication. This could be a journal article, for example, in the American Society of Composites, or it could be a scientific article like in Berkeley Engineering. Something else I'm really into at the moment is teaching, and this is something that's probably in your future as well as engineers. This involves a lot of technical writing, which I hear is one of the key themes of these green talks here today. I really enjoy technical writing because it enables you to not only get across your science, but also to tell people some pretty interesting stuff that maybe they wouldn't have found out otherwise. And all of this fits into technical communication. And that's the role I do at UC Berkeley in terms of teaching, helping teach the Masters of Engineering, which I'm sure all of you will be progressing towards soon. So while we have this overall theme of materials research, technical communication, destructive testing, the key theme that's moved through it all from my undergraduate through my master's onto my PhD is communication. And what may surprise you is that I didn't actually start in America on my PhD in mechanical engineering. I actually came here for sign language. Now, many years ago, I got interested in sign language as I saw it being demonstrated, and I just thought it was really cool. So I decided to learn British Sign Language. I then discovered there's actually a different sign language for each country in the world, and American Sign Language is actually different. So I decided to come to America and study a bit of American Sign Language. Through that process, through random connections, I then eventually got tracked onto a PhD in mechanical engineering, and now I enjoy using my communication skills, mostly verbal, to build links between the scientific and commercial community. As we all know, here in the Bay Area, San Jose, Mountain View, San Francisco, Richmond, and even the neighboring states, engineering is one of the fastest growing sectors. There's only so many engineers in the world, and so all of us here will have important roles to play in future industry. This means our work that we do, and even mushroom research, gets really connected to the industry in the Bay. And as a result, I've enjoyed the opportunities of meeting startups in the San Francisco area, such as IndieBio, which has also been really exciting. So that's something you might not know about a PhD, is you get lots of different experiences through it. Something I'm also fascinated by is infographics. What I like to do is basically get information and put it across in the easiest way possible. I thought you might like an example. So here's some of the information that we're doing currently on the Masters of Engineering. Students have a whole set of things they need to do, presentations, meetings, all sorts of bits and bobs. Now, I find this a bit awkward to look at. I don't know about you, but it doesn't feel very intuitive to me. Communication is all about getting across your information in the best way possible. I like to reprocess these into a visual format. Same information, but presented in a different way. This is really key for PhDs, because while you might think they're very scientific and it's all about laboratory work, actually they're all about being able to communicate your work to your professors, to your advisors, and to the wider community. So now that I've talked all about my general academic journey and how I came to be here talking to you today, we should get right back to the mushrooms. So let's look a little bit deeper into them. What are they actually made of? What makes a mushroom? Well, mushrooms are made of chitin, and that's a cellular material. Now, I'm going to talk at length about cellular materials, but first, let's learn a bit more about chitin. It is an organic molecule, so it's made of completely natural components, your carbons, your hydrogens, your oxygens, and your nitrogens. Chitin is fascinating because although it's a natural material, and you can think of it as being in crustaceans or those shiny beetle shells, if you think of the iridescent hard shell of beetles, that's what chitin is. What's interesting is that it can take on very different formats. It can be quite a soft, almost fluffy kind of material. But arranged slightly differently, it can become a very hard, very dense, quite strong material. And this is important, as when you're making materials, you can actually use different types of materials in order to get different properties. So, for example, the interior of this material could be very lightweight, very fluffy, very low strength. But the exterior could be made really hard and able to withstand lots of wear and tear. Now, this is unusual in natural materials because generally, natural materials are not considered engineering-ish. If you think of materials that you might want to build with, you might think of concrete, maybe glass fiber, or perhaps some metals like aluminium. You probably wouldn't think of mushrooms. But through engineering them, we can actually turn them into a useful material. We can do this by partly reinforcing them. So while these materials on their own might not be as strong as we want them, you can combine different materials to get the exact properties you want. Now let's talk about this cellular structure. Now, what do I mean by cellular structure? A cellular structure means that each part of the material is formed into little repeating blocks. Why is this important? Well, cellular materials have some really handy things about them. For a start, they're very efficient in terms of strength. Instead of making a solid block of material, you can make it into cells. And this means that the reinforcement is through the cubic sides, the structure that you have of those individual cells, and the majority of space in there is actually open pockets of air. That's kind of important for insulation, which I'll mention later. These materials are actually modeled as an open-celled foam. So if you imagine a cube, and the cube is empty, the struts that the cube made are made of chitin. And if you size that up from the microstructure, bigger and bigger into the macrostructure, eventually you get a mycology material. So let's delve down. Let's go into the microscopic level and see what these are actually made of. So here we have some mushrooms. This is a Ganoderma lucidum sample, and it's actually a chair, would you believe? So we've zoomed in on that. let's look a little bit closer. This is scanning electron microscopy, which basically you're firing electrons at a sample, and you're able to visualize it just like a microscope, but using electrons. So this material you're seeing right now is this material right here, just really small. Now, as you can see, it's almost got a random mat cellular structure. So the structure is very devolved, it's very randomized, everything's going everywhere. But once it keeps on growing, you can start to see the fact that it's effectively making these little pockets, these repeating structures of cellular material. Let's zoom in a little more. One of these strands, which is known as a hyphae, which is kind of one of the growing parts of a mushroom, like when you have a mushroom, lots of little threads kind of combined together as its roots, that's its hyphae. One of these is really only about 1 micrometer. That's pretty small. That's around 1/10 of a human hair. So individually, these biomaterials on the micro scale are very, very small and really quite weak. But if you combine them together and allow them to grow into a cellular material and then edit their properties and grow them in a way you want them to, they can actually form something strong enough to be a building material. So now that we understand what these mushrooms are actually made of, what do we do with them? Well, that's what we decided to find out. And that's the bit that I'm really interested in, the mechanical properties. So the first thing we looked at was their strength. Just how strong is a mushroom? Well, quite strong is the answer. What we did is we turned it into samples. So that was one of my jobs as a PhD student, is to go into a lab and actually carve this material up using bandsaws, which is quite exciting, and to form lots of different samples that I'm going to use for testing. And then we started to look at their strength. You might have done these tests already yourself in your degrees. We looked at tensile strength and compressive strength to see exactly how much force it could withstand squishing it and stretching it respectively. What we found is that these materials are roughly comparable to soft woods. So if you think of your balsa woods, your pine, that's what we're looking at. But they're much, much lighter. Again, lightness in engineering is really important, as weight saving equals money saving when you're designing. So finding a lightweight but strong material is really something engineers are always looking for. Now, these materials are quite strong, but maybe not strong enough. When we want to make a material even stronger, we don't just have to add more weight. You can actually make a sandwich composite. Now, I'm very interested in composites because that's what I first studied in my master's and PhD. And if you haven't heard of what a sandwich composite is, what you do is you get two dissimilar materials, perhaps something that's very light but not very strong, and something that's quite heavy but quite strong, and you cross them together, and you get a mix of the best of the two properties. So you get something light and strong. Sandwich composites use this in particular by getting two different materials and layering them together. So, just like a sandwich, the filling of the sandwich would be the Mycology material, which is very light, very insulative, and provides plenty of tough structure without too much weight. And then you could actually put a skin on top of it, the bread of that sandwich, which can make it nice and strong and give you the strength you need. Now, you could go with something synthetic. For example, carbon fiber, quite expensive, glass fiber, cheaper. Or you could even go with another natural material. An analogy to carbon fiber in the natural world is bamboo. Bamboo is actually really axially strong, just like carbon fiber, so that means it can take lots of strength in its axial direction. If you combine these two together to make a sandwich composite, you'll have a strong, tough, and light material, all made from mushrooms. Now, as I said, these cellular materials have lots of air pockets in them. This naturally lends them to being great insulators. a lot of the civil engineering materials used have to basically insulate heat. This is particularly important in England where it is very chilly, and so we insulate all of our buildings heavily. Here, kind of the opposite problem. It's pretty warm, so you insulate to keep things cool. We tested this material to see just how insulating it was. That was quite fun to do because we basically put it next to very hot things and saw how much heat would transmit across. We also set fire to it, and the answer is it doesn't burn very easily. One thing that we found is that it's basically comparable to balsa wood or softwoods in terms of its resistance to passing heat along, which you may already know about from your thermodynamics classes. Some advantages, though, is that typically insulative materials such as glass fiber are really quite expensive. Glass fiber itself, you have to process many different types of chemicals, you have to refine lots of chemicals, bring those together, manufacture the product, quite a lot of energy in that. But a biomaterial does that all itself. At the same time, it's digesting waste in order to make that material. So in insulation, that's not only low cost because you're saving all of that effort and energy, but also totally natural, because if you've ever actually used glass fiber or carbon fiber, it's kind of a hassle to use. You have to have a lot of PPE, personal protective equipment on, whereas when working with biomaterials, other than your standard PPE, it's much easier to work with. People also tend to prefer natural materials. Although plastics are fun and they can be produced in many different ways and they're great for really specific high-tech applications, when we want to interface with a material, we tend to like biomaterials and natural materials because they're pleasing, like wood or marble. And of course, at the end of that entire life cycle, it goes into its disposal phase. All products, even the ones that we use to make civil engineering applications such as building, have to eventually be disposed of. And when you're designing a particular material or a product, that's something we have to be cognizant of. So being able to recycle a material basically means that you save a lot of effort. So now that we've talked about what these materials are, what they're used for, how they're made, and what they're comprised of, let's talk a little bit more about what they're actually used for. Well, right now, there's actually a few uses already. Here on the West Coast, we have Mycology, who we actually collaborate with. They're based in San Francisco. And they turn these materials into actual artifacts. So this is a table, and on the interior is this exact material here, this Mycology material. And you can think of it rather like the sort of material that's inside IKEA tables, that kind of crumbly wood, compressed wood kind of thing. But we don't really want a table that has such poor surface qualities. No one wants to put their cup of tea down on something that's not easy to clean. So we then make a sandwich composite. We face it with something that's really quite pleasing to the touch and would really suit itself to everyday use. This is bamboo. As I mentioned, bamboo is very strong in its axial direction along the length it grows. And it's also very easy to machine, so you can machine it down to very good tolerances. This means it's really good to build stuff with because you're able to use it in quite delicate dovetail applications, as you can see here. Some of the other artifacts made by Mycology include more sort of artisan creations, such as this one. This is actually a chair made, as well as the table, were made by Professor Philip Ross of Mycology. And as you can see, this is much more of an artistic application. I'm not sure we'd all want to sit on this chair. But as you can see, it kind of combines together lots of different natural materials, and the fact that this could be placed into a compost heap and turn entirely back to soil is really, I think, quite fascinating. This is really a concept that could be extended quite far. They've even proposed making houses out of this material. And there's other people working in this space as well. Out on the East Coast, we have Ecovative. They've been making packaging from this. Now, packaging is a really good idea Because packaging, you use it, it needs to be able to be tough, take lots of force and be able to deal with that without breaking. It also needs to be low cost. You don't want to pay hundreds of dollars just to have some packing peanuts. And most importantly, what do you do with packaging? You throw it away once you're done. So it needs to be recyclable. Now, recyclable and compostable are quite different things. Recyclable is good for synthetic materials that are so high energy, we want to keep that energy in circulation. But natural materials have another alternative. They can be composted. So instead of retaining the material, we allow it to totally dissolve back to nature. This effectively turns back into soil. It goes back to those carbons, hydrogens, nitrogens, and oxygens that make for your basic biomaterials. You could then come along, take that carbon-containing material, introduce new mushrooms to it, and grow another material. This means mycology materials have quite an unusual property, as in they're almost a closed-loop cycle. So the energy and material that you put in can simply continuously be recycled through disposal and then used again to make another material. So where are we going with these materials? What could they do for us in the future? Well, companies all over the US are continuing to develop them. They're making all sorts of new commercial applications for them. People are very interested, as I said, in insulation, because these materials really lend themselves to that. We're also looking at all sorts of different materials and products we could replace using these. So, for example, a lot of wood is used in commercial products, not only for furniture, but also in construction in America. And this is something that's really quite energy intensive. Wood takes a very long time to grow. It has to have a fair amount of space to grow it, and also logging. So there's environmental impacts to that. Whereas if you were using a mycology material, literally growing a material from mushrooms, not only could you grow it in a much more condensed space than an entire forest, but you could also remove those environmental impacts that logging and deforestation cause. So really there's a lot of interesting applications for this material, and we're still finding more. It's in its very first stages of research, and it's been a real pleasure at UC Berkeley to be able to be part of founding that field of mycology research. And that's what I'm currently focusing on. I've been doing all sorts of different testing, such as testing laminates of these materials, flame resistance, as I mentioned, setting fire to it, the destructive testing for strength. We also looked at how long this material could survive when placed outside. How long does it take to degrade? Writing all of that up has been really fun as part of my PhD. And also it gives you an opportunity to connect to many different fields, which you probably wouldn't have done so otherwise. For example, the industry around the Bay Area and interesting colleges like I'm speaking to here today. So looking into the future, there are a real multitude of uses for these mycology materials. They offer a much lower environmental impact. They're totally recyclable and entirely made of natural materials. Overall, they offer us a really inspirational option for biomaterials. So it has been a pleasure talking to you today here at San Jose State University, and I would like to say thank you very much.
Thank you, Sonia. So, questions?
Ooh.
Oh, we've got to get it on the microphone.
Thank you.
So you showed a picture of the slab you cut up with the saw and stuff like that. On a time scale, how long would it take to produce a sample that size?
And a sample of this size?
Yeah.
These tiny bricks here, I would say, will take around a week. So it's very, very quick growing. This block here, which you can kind of think of as standard foot-long brick of this material, that takes only around 2 to 3 weeks from the time it very starts growing to ending up this kind of block of mushrooms here. So it is very fast growing.
Do you have to worry about the, is the material actually still alive in this case? Like, I know that usually with wood, the material we use is dead at that point. But do we have to worry about, like, maintenance and, like, applying nutrients and other stuff to maintain it?
What an excellent question. That is a really important key point about this material, is that when we grow this material, it is a live, natural growing thing. So you probably don't want that growing in your house. What we do, or maybe you do, but that's your own choice. What we do is we put it into an oven and we bake it like a cake. We'll take it up above 70 centigrade, which denatures any natural kind of organic material, and then the material is basically, for all intensive purposes, dead. But you're absolutely right. In order for it to be a material that's safe to go into a commercial application, it has to be denatured.
Sorry.
We have a question over here.
So after you do the heat treating process and then you build this into, say, a table, what is the lifespan that you're looking at for, say, commercial material?
Another great question. How long do these materials live? Well, this was one of the topics we investigated, I think last year or the year before last in a publication. Google them, they are out there. Completely untouched, as in not faced with anything, not covered in anything, not coated in anything. These materials last around a month just outside. So if you just leave them in your backyard, it takes about a month for them to start experiencing any sort of degradation. That's completely natural though, that's uncovered. What we do recommend is covering them with something, either another laminate such as bamboo, or you could water seal them, because obviously you don't particularly want wooden products getting wet because their dimensions change. And the same for biomaterials, you want to keep them nice and dry. So you can then coat it in something like shellac if you want a nice hard natural material, or something like natural latex if you want it to be waterproof but not particularly hard. Once they have been coated, in terms of stopping any water getting in, pretty much indefinite so far, since I've been researching them anyway. Question?
So out of like all the kinds of different like fungi, how did you manage to choose this one in particular?
Another awesome question. How did we decide to come on to Ganoderma lucidum? Well, basically, there are a crazy amount of mushrooms in the world. There's all sorts. There's mushrooms that are digesting wood. There's mushrooms to digest plastic. We'll get there in a moment. But in particular, we use this one, Ganoderma lucidum. We chose this because it's a very common mushroom. Reishi, as it's kind of colloquial known, is not only used in healthcare, it's considered to have anti-cancer properties, surprisingly. So we picked a very common mushroom that would be easily accessible, easily able to get the exact genome in order to grow it. But really, good question, because what type of mushroom do you want? There's even mushrooms that can digest plastic. So you can literally put some plastic in a box with some mushrooms, and it will digest the plastic and turn it into a material. So basically, you pick the mushroom of the particular type of material you want. And some of these can grow to be light and fluffy. Some of them can grow to be really hard and compact, really dense. Oh, question.
Mic test. Have you heard of aerogels?
I have.
Do you expect having your product or going down to that level of weight and strength? Is that even possible with organic materials?
That is a fascinating thought. I mean, I'd love to get down to something as light as an aerogel. If you've never seen an aerogel, it really looks like you're holding a cube of smoke. And they're actually so comprised of air that they're virtually weightless while being still quite strong. I think in terms of where we could get to with the fungi, could we turn this into an aerogel? Probably with enough effort you could get to extremely lightweight, but I'm not sure you could approach something synthetically manufactured. Nature always has a sort of minimum level that it needs to be able to operate at, because it is a living material. When this grows, it is transmitting information through its network, it's transmitting water, it's transmitting nutrients. So that at a basic level does make a microstructure which probably couldn't get to an aerogel kind of lightness, but considering already the very great strength to weight ratio, who knows where we could get it to.
I just want to know, is there a cost benefit to using the fungi?
Yes, the question is, for the recording, what's the cost benefit?
Basically, the cost benefit is in terms of saving your feedstock. So if you imagine a plastic, if we're creating a component, this is probably ABS, acrylonitrile butadiene styrene, ABS. When you have to produce this material itself, you have to not only extract the oil from the ground, you then have to refine that into different petroleum-based products. You have to then extrude it, all of this. That's quite a heavy cost in manufacturing, and typically puts a heavy dent in that life cycle analysis. With natural materials, really, they just do it all for you. Not only do they go off and find their own feedstocks, which are not oil-based, which is important, they basically assemble it themselves, form into the morphology they want, so you save all of that effort. Something I should mention is that these can be grown into any dimensions you want. So we've grown them quite small, but the fungus structures can grow to massive because they are devolved networks. So that cellular material can pretty much get as big as you like. They also grow into any dimension that you mold them into. So you could produce a mold of the particular shape you wanted, have the material grow in it, and it will take on those dimensions. So then you could even save yourself the effort of having to do the shaping processes too. So the cost benefit is basically no feedstocks, especially not oil-based, saving a lot of that manufacturing cost, and then you even save at the other end as well on disposal.
So this is a mold, this is not compressed.
That's correct. This has just literally been in a square-shaped mold with the feedstock, which is sawdust, effectively, for this type of mushroom. And then the mushroom goes along, eats up all the sawdust, and takes up the shape that it's in.
Would there be any value to compressing it further, or is the natural structure this kind of its strongest point?
You can reprocess them to get a different morphology. So when they first start off, they tend to be quite light, fluffy structures, because in nature they don't particularly need to have a lot of compressive strength. But you can process them as they're growing to heighten their ability to be strong. You can't really compress them once they're already made, because they're actually really quite hard to compress.
Well, with that, I'd like to thank you for a fascinating talk, Sonia. Thank you.
Thank you very much.
So thanks, everyone. I'll see you next week, and I'm sure Sonia will be around for at least 15 minutes if you want to chat with her.